Good evening. On this channel, I guide you to stars and other interesting objects nearby in our galaxy. I'm an AI voice, just so you know, but I hope you like me anyway. In this first ever episode, we will travel to Alpha Centauri, the closest star system to the solar system. Alpha Centauri is a triple star system with a main binary of 2 sun-like stars and 1 small red dwarf orbiting the binary far away, forming a trinary. It consists of Rigil Kentaurus, also known as Alpha Centauri A, Toliman, also known as Alpha Centauri B, and Proxima Centauri, also known as Alpha Centauri C. Rigil Kentaurus and Toliman are bright, yellow-orange stars similar to our own Sun, while Proxima Centauri is a red dwarf star. Proxima Centauri is too faint to see without a telescope. The distance to Rigil Kentaurus and Toliman is about 4.34 light-years, and the distance to Proxima Centauri is about 4.25 light-years. Proxima Centauri is the closest star of all stars to our Sun. The name Alpha Centauri was given by Johann Bayer in 1603. The older name, Rigil Kentaurus, is of Arabic origin and means the foot of the centaur. Toliman was another name used historically, also of Arabic origin. Today, the International Astronomical Union, IAU, has decided that Rigil Kentaurus refers to Alpha Centauri A, and Toliman refers to Alpha Centauri B. For the sake of simplicity, I will talk about Alpha Centauri as one star, unless I refer specifically to any of the 3 gravitationally bound stars of the system. The distance to the center of mass of the Alpha Centauri system is about the same as main binary system and will be referred to as 4.34 light-years from Earth. The main binary system can also be treated as a single gravitational object since the distance between Proxima Centauri and each of Rigil Kentaurus and Toliman is about the same. Alpha Centauri can be seen in the southern hemisphere in the constellation Centaurus. To the naked eye, the binary star system of Rigil Kentaurus and Toliman looks like one star. It is the 3rd brightest star in the night sky, after Sirius and Canopus. Relative to Earth, it is in the plane of the Milky Way, and in fact close to the center of the Milky Way. It is often used as a reference point to locate other stars and celestial objects in the southern night sky. Alpha Centauri never sets below the horizon viewed from below 29 degrees south latitude, that is, some southern parts of Chile, Argentina and Brazil, the southern tip of South Africa and some parts of Australia. In fact, the border between Queensland and New South Wales, of Australia, is partly defined by this line. Then, on the other hand, if you go north of 29 degrees north latitude, Alpha Centauri never rises. So you must go south of that point, like south of Houston, Texas, or south of the Canary Islands of Spain, to catch a glimpse of Alpha Centauri at least some time of the year. When viewed with binoculars or a small telescope, Rigil Kentaurus and Toliman might still appear as a single point of light due to their close proximity. The colors of the stars, yellowish for Rigil Kentaurus and orangish for Toliman, may not be clearly distinguishable with low magnification. Observers using a high-powered telescope might be able to resolve Rigil Kentaurus and Toliman as 2 distinct stars. The binary star system of Rigil Kentaurus and Toliman orbits each other, or in other words a common center, about every 80 years. The distance between them varies somewhat but is approximately like the distance between the Sun and the outer planets of the solar system. Their elliptical orbit is eccentric, so that the distance between them varies from 35.6 astronomical units, or about the distance between Pluto and the Sun, to 11.2 astronomical units, or about the distance between Saturn and the Sun. Proxima Centauri, on the other hand, is believed to orbit the 2 stars much farther away with a period of more than 500,000 years. In the night sky, Proxima Centauri is located about 4 times the angular diameter of the Moon to the southwest of Alpha Centauri. The actual distance between Proxima Centauri and Rigil, Kentaurus and Toliman is about 5% of the distance between Alpha Centauri and the Sun, that is, about 13,000 astronomical units. With our current technology, traveling to Alpha Centauri would take tens of thousands of years, even though it is the closest star to Earth. In the future, however, if it would be possible to reach, say, 10% of the speed of light, it would take about 50 years to reach Alpha Centauri from Earth and then receive a signal. Alpha Centauri, given its status as one of the closest star systems to Earth, has figured prominently in various science fiction and popular culture contexts. Here are some examples. Literature. Isaac Asimov's Foundation series mentions Alpha Centauri several times as humanity spreads out through the galaxy. And in the Songs of Distant Earth by Arthur C. Clarke, Earth sends seed ships to Alpha Centauri in an attempt to preserve human life before the sun goes nova. Television and film. The film Avatar is set on Pandora, a habitable moon of a gas giant in the Alpha Centauri star system. And in Lost in Space, the Alpha Centauri system is the target destination for the colonizing mission central to the plot of the series. Video games. The strategy video game Alpha Centauri, by Sid Meier, involves factions of Earth colonists settling and vying for control on a planet in the Alpha Centauri system. And the Mass Effect series frequently mentions Alpha Centauri as a location within the game's expansive universe. As mentioned, Alpha Centauri can be seen in the constellation Centaurus, named after the mythological figure of Centaurus. The constellation Centaurus is one of the largest and most prominent constellations in the southern sky. It holds a great deal of interest both for its bright stars and the various celestial objects it hosts. Centaurus is often depicted as a centaur, a mythical creature with the upper body of a human and the lower body of a horse. In Greek mythology, one story identifies the centaur in the stars as Chiron, known for his wisdom and healing abilities. Chiron was placed among the stars by Zeus, immortalizing him in the night sky. In Centaurus, you can also see Beta Centauri, a giant binary star system and the 11th brightest star in the night sky, known for its blue-white hue. Another notable object in Centaurus is Omega Centauri, a globular cluster that is one of the largest and brightest known, easily visible with the naked eye under good conditions. And you have Centaurus A, NGC 5128, an active galaxy noted for its impressive radio emissions and a notable dust lane bisecting it. The two brightest stars of Centaurus, Alpha Centauri and Beta Centauri, are commonly referred to as the pointers. They are used to locate Crux, the Southern Cross, a smaller but significant constellation for Southern Hemisphere navigation. There are several other stars that are quite close to Alpha Centauri in space, compared to the Sun. The closest one is Lumen 16, at a distance of about 3.62 light-years from Alpha Centauri. It is a binary system of brown dwarfs in the constellation Vela. Lumen 16 is the closest known brown dwarf system and the third closest known star system to the Sun. Another close one is Barnard's star at about 3.58 light-years distance from Alpha Centauri. Barnard's star is a red dwarf star in the constellation of Ophiuchus and is the fourth nearest known individual star to the Sun, or second closest star system to Earth. Wolf 359, about 4.62 light-years from Alpha Centauri, is found in the constellation Leo. Wolf 359 is a red dwarf and one of the faintest and lowest mass stars known. Further, the stars Sirius, Lalande 21185 and Ross 154 are all within 6 light-years from Alpha Centauri. Alpha Centauri was likely known to ancient observers in the southern hemisphere. However, explicit records from ancient civilizations are scarce or non-definitive. Due to its brightness, it would have been used for navigation and timekeeping by various cultures. The system was introduced in the 16th century to the European astronomical community by explorers and navigators traveling in the southern hemisphere. Alpha Centauri was likely observed in 1592 by the Portuguese explorer and navigator João Holman, who was part of a fleet to India, and recorded a star in the position close to the actual location of Alpha Centauri. However, this record is not definitively attributed to Alpha Centauri. In 1689, the Italian astronomer Giovanni Cassini documented the position of Alpha Centauri, though it had likely appeared in earlier European star catalogues without detailed notes. Also in 1689, Jean Richards discovered Alpha Centauri's binary nature. Richard's observation occurred during a session in which he was monitoring a comet from Puducherry. This was a pivotal moment in astronomy since it was only the second binary star system ever identified. In the 19th century, the German astronomer Hendrik Bessel was one of the first to notice that Alpha Centauri had a wobble in its proper motion, suggesting that it might have a companion. Later, it was conclusively determined that Alpha Centauri was a binary star system, through the detection of binary motion and the notable difference in the color of the two components. Scottish astronomer Thomas Henderson, working at the Royal Observatory at the Cape of Good Hope, was the first to measure the parallax of a star in 1839, demonstrating stellar distance, and the star was Alpha Centauri. Proxima Centauri, the smaller companion invisible to the naked eye, was discovered in 1915 by Scottish astronomer Robert Innes, director of the Union Observatory in South Africa, while he was studying the binary system. He observed a faint star that shared the same proper motion as Rigil, Kentaurus and Toliman, and subsequent studies confirmed its proximity and association with the Alpha Centauri system. Over the subsequent decades and into the 20th century, Alpha Centauri has been the subject of a wide array of astronomical studies, given its closeness and similarities to our own Sun, particularly when it comes to Rigil Kentaurus. This has included detailed spectroscopic, photometric, and astrometric studies, among others. Alpha Centauri's motion through space, when observed from our solar standpoint, can be dissected into various components, like radial velocity, which is its speed directly towards or away from us, and proper motion, its apparent traverse across our sky. The system exhibits a radial velocity of about -22.2 kilometers per second, meaning it is moving towards our solar system. As we contemplate the motion in a broader, galactic context, Alpha Centauri does not voyage through the cosmos in isolation. Our Milky Way galaxy, a grand spiral entity, orchestrates a collective motion of its stellar inhabitants, guiding them along paths dictated by gravitational dynamics and the distribution of dark matter, among other factors. The Sun, too, orbits the Milky Way's center, traveling at an approximate speed of 230 kilometers per second along a trajectory that influences the relative motion observed for stars like Alpha Centauri. The proper motion of a star refers to its apparent motion across the sky as viewed from Earth, expressed in terms of angular movement per year. The proper motion has two components: motion in right ascension, or east-west direction, and motion in declination, or north-south direction. Alpha Centauri has a noticeable proper motion due to its proximity to Earth, moving approximately 3.7 arcseconds per year across the sky. Over years and decades, this proper motion results in a noticeable shift in the position of Alpha Centauri in the sky, which can be mapped and predicted. The proper motion of Alpha Centauri must be accounted for in various astronomical observations and calculations to ensure accuracy. The proper motion of the Alpha Centauri system is further complicated by the orbital motion of Rigil, Kentaurus and Toliman around their common center of mass, which introduces additional relative motion. The proper motion of Alpha Centauri, as with any star, will cause its position in the night sky to change gradually over time. These changes will be observable to humans over centuries and millennia, altering the appearance of the star field in its vicinity. Over tens of thousands of years, the proper motion of Alpha Centauri will be significant enough to alter the shape of the constellation Centaurus. Predicting the exact position of Alpha Centauri in the very distant future, up to tens to hundreds of thousands of years, is challenging due to several factors. The gravitational interactions between the main binary system and Proxima Centauri could introduce perturbations into their paths. Further, the star system, along with our Sun, is moving around the center of the Milky Way, which introduces additional dynamical complexities. Interaction with the interstellar medium and potential close approaches to other star systems over extended timescales could also influence its trajectory. However, projecting to around 6200 AD, an exceptionally rare astronomical event is forecasted. Alpha Centauri will form an incredibly bright optical double star with Beta Centauri due to its true motion, presenting a stunning first-magnitude stellar conjunction in our southern sky. Subsequently, Alpha Centauri will traverse just to the north of the notable Southern Cross, or crux, thereafter veering northwest and ascending towards the contemporary celestial equator, concurrently distancing itself from the dense plane of our Milky Way galaxy. Roughly by 26,700 AD, and within the modern-day boundaries of the Hydra constellation, Alpha Centauri is expected to reach its perihelion, being nearly 0.90 parsecs or 2.9 light-years away from the Sun, although later computations suggest this milestone might be more accurately positioned around 27,000 AD. In its closest approach to our solar system, Alpha Centauri will shine with a peak apparent magnitude of -0.86, rivaling the current brilliance of Canopus. Yet, it won't outshine Sirius, which itself will gradually brighten over the ensuing 60,000 years and will retain its title as the brightest star visible from Earth, excluding our Sun, for an estimated 210,000 years. A concept known as a moving group or stellar association suggests similar origin of a local group of stars including the Alpha Centauri system. The stars HD 4391, Gamma 2 Normae, and Gliese 676, along with Proxima Centauri, Rigil, Kentaurus and Toliman, are exhibiting a similar spatial motion. Their space velocities, which are within 10 kilometers per second of Alpha Centauri's peculiar motion, that is, a star's motion relative to the average motion of its neighbors, suggest they might be part of a moving group. What's particularly noteworthy here is the implication of these stars' common motion. Stars in a moving group were likely formed in the same molecular cloud and were subjected to the same cosmic conditions. Over time, these stars could have dispersed from their initial cluster, due to gravitational interactions or other influences, while retaining a semblance of their original shared motion. If these stars do indeed form a moving group with the Alpha Centauri system, it would suggest that they originated from the same star cluster. This common point of origin can offer invaluable information about these stars. For instance, it may provide clues about their ages, compositions, and histories of their solar neighborhoods. It also helps astronomers understand the dynamics of the Milky Way and how star clusters contribute to star dispersion throughout the galaxy. Given that Alpha Centauri as viewed from Earth is in the plane of the Milky Way and close to the more densely packed center of the galaxy, many stars appear behind it. A significant astronomical event involving Rigil Kentaurus is anticipated to occur in 2028. In May of that year, Rigil Kentaurus is expected to pass very close in the night sky to a distant background star, a phenomenon known as a stellar conjunction. This event has garnered interest in the astronomical community due to the possibility that it might create an Einstein ring. An Einstein ring is a gravitational lensing phenomenon predicted by Einstein's theory of general relativity. It occurs when a light source, a lensing mass, like a star, and an observer are all perfectly aligned. The gravitational field of the lensing star, Rigil Kentaurus in this case, bends and focuses the light from the more distant star, potentially creating a ring of light around it. These events are precious to astronomers as they can be used to test theories of gravitation and gain insights into the properties of the involved stars. Specifically, for the 2028 event involving Rigil Kentaurus, scientists believe that it presents a unique opportunity to get a measure of the star's mass more accurately than ever before, thanks to the gravitational lensing effect. Furthermore, if planets are orbiting Rigil Kentaurus, their effects might also be detectable in the light curve of the event, possibly providing a method to confirm the presence of any otherwise undetectable planets. The terms apastron and periastron pertain to the orbital parameters of an eccentric orbit such as that of Rigil Kentaurus and Toliman around their common center of mass. Periastron is the point at which two stars in a binary system are closest to each other during their orbit. For Rigil Kentaurus and Toliman, their orbits vary due to gravitational interactions, but their periastron distance is typically just under 12 astronomical units, slightly greater than the distance between Saturn and the Sun in our own solar system. Their closest approach in recorded history was 11.2 astronomical units in August 1955. Conversely, a pastron is the point of greatest separation between two stars in a binary system. For these two stars, the apastron is approximately 35 astronomical units, which is roughly the distance between the Sun and Pluto on average. The farthest distance in recorded history was 35.6 astronomical units in May 1995. The orbital period of Rigil Kentaurus and Toliman, that is, the time it takes for them to complete one orbit around their common center of mass, is about 80 years. Their orbit is, of course, not a perfect circle but rather an ellipse, with an eccentricity of 0.52, indicating a notable departure from a circular shape. Viewed from Earth, however, what we see are the orbits at an angle. The observed maximum separation of these stars is about 22 arcsec, while the minimum distance is 1.7 arcsec. The widest separation occurred during February 1976, and the next will be in January 2056. These changes are way too small to be noticed by the human eye. As for Proxima Centauri's orbit around Rigil Kentaurus and Toliman, it has not historically been a given that it was gravitationally bound. If Proxima Centauri is indeed in orbit around Rigil Kentaurus and Toliman, it is a wide one, and with a lengthy orbital period that extends over 500,000 years. The gravitational binding energy needed to hold Proxima in orbit around Rigil Kentaurus and Toliman, given its current velocity and distance, sits on the brink of what is plausible, leading to some uncertainties and debates among astronomers. Until 2017, measurements of its small speed and its trajectory were of too little accuracy and duration in years to determine whether it is bound to Rigil Kentaurus and Toliman or unrelated. But radial velocity measurements made in 2017 were precise enough to show that Proxima Centauri is most likely gravitationally bound. The orbital period of Proxima Centauri is approximately 500,000 years, with an eccentricity much like that of the main binary orbit of 0.5. At periastron, its closest approach, the distance to the main binary system is about 4,000 astronomical units, and at its apostin, when it is the farthest apart, the distance is more than 12,000 astronomical units. At present, Proxima Centauri is close to apostin, that is, the farthest point in its orbit, and in fact close to 13,000 astronomical units from the main binary. Proxima's trajectory through the cosmos is influenced by its initial velocity, the gravitational pull of the Milky Way, and the gravitational interaction with Rigil, Kentaurus and Toliman, if it is bound. Gravitational effects from the galaxy itself and other nearby stellar or interstellar entities further complicate the dynamical scenario, introducing perturbations that can modify Proxima's path. Proxima Centauri, the closest known star to the Sun, has held this status for approximately 32,000 years, and it is projected to maintain this proximity for around another 25,000 years. Following this period, the primary components of the Alpha Centauri system, Rigil, Kentaurus and Toliman, are expected to take turns being the Sun's nearest stellar neighbors, alternating approximately every 80 years as they orbit their center of gravity. The study of the orbits, such as understanding the periastron and apastron distances, holds substantial importance. It allows astronomers to compute the masses of the stars via Kepler's laws, contributing to our understanding of stellar evolution and mechanics. Additionally, understanding these parameters is crucial for any observational or exploratory missions targeted at the Alpha Centauri system, as they dictate the relative positions and distances of these stars over time, affecting gravitational influences, observational characteristics, and navigational calculations within the system. Moreover, the complex gravitational environment created by the binary nature of Rigil, Kentaurus and Toliman also presents intriguing questions and challenges for the study of planetary systems within binary star systems, affecting planetary formation, stability, and potential habitability in ways that are still subjects of ongoing research. Let us now have a closer look at Proxima Centauri in particular. Like we said, Proxima Centauri is the nearest star of all stars to the Sun, and therefore it was named Proxima Centauri. Proxima means nearest in Latin. Proxima Centauri has a mass of approximately 0.12 solar masses. This relatively low mass places Proxima Centauri within the category of red dwarf stars, which are some of the most common types of stars. Red dwarfs like Proxima Centauri make up about 70 to 80% of all stars in the universe. Their low mass means they have a considerably longer lifespan than larger stars since they exhibit slower rates of nuclear fusion in their cores. This slow burn is due to lower pressures and temperatures in their cores, compared to larger stars like our Sun. Proxima Centauri has a radius of approximately 0.14 solar radii, or about 1.5 the size of Jupiter. To provide some perspective, if the Sun were the size of a basketball, Proxima Centauri would be roughly the size of a ping-pong ball. Given its mass and volume, Proxima Centauri has a higher average density than our Sun. The internal pressures and gravitational forces at play are in any case substantial, driving the nuclear fusion processes that power it. The effective surface temperature of Proxima Centauri is estimated to be around 3000 Kelvin, which is equivalent to about 2800 degrees Celsius or 5000 degrees Fahrenheit. This temperature is much cooler than our Sun, which has an effective surface temperature of around 5800 Kelvin, equivalent to about 5500 degrees Celsius or 9950 degrees Fahrenheit. The cooler temperature is consistent with its classification as an M-type dwarf star. The Stefan-Boltzmann law tells us that a star's luminosity, indicating its total energy output, is directly proportional to its surface area and the fourth power of its temperature. Given Proxima Centauri's low temperature and small size, its luminosity is a fraction of our Sun's, making it invisible to the naked eye despite its proximity. Compared to the Sun, Proxima Centauri is 20,000 times more faint. The apparent magnitude of Proxima Centauri is approximately plus 11.05. The lower the magnitude number, the brighter the object appears to observers on our planet. To provide context, the faintest stars visible to the naked eye under ideal conditions typically have an apparent magnitude of about plus 6. Objects with magnitudes greater than plus 6, like Proxima Centauri, generally require telescopes or binoculars for observation. Further, 85% of its emissions is in infrared, beyond the visible spectrum. Planets in its habitable zone would therefore receive a different spectrum of light compared to Earth, which could influence processes like photosynthesis in hypothetical plants. If life exists on planets around red dwarfs, it might have to adapt to this redder light, potentially leading to intriguing biochemical differences. The red in red dwarf is a direct nod to the cooler temperatures, which produce a reddish hue. The reddish hue of Proxima Centauri is a characteristic color of cooler stars. A star's color is intrinsically tied to its surface temperature. Cooler stars, like Proxima Centauri, emit light that peaks in the red or infrared part of the spectrum. Conversely, hotter stars can appear white or even blue. The progression from red to blue stars with increasing temperature is a direct application of Wien's displacement law, which states that the wavelength, or color, at which a black body spectrum is maximized is inversely proportional to the temperature of that body. Stellar temperature is not indicative of calmness or stability, however. Despite its cooler temperature, Proxima Centauri is, like red dwarfs in general, known for violent flares and significant magnetic activity. During these flares, the star can temporarily become many times brighter, and its color can shift, becoming whiter due to the increased temperature associated with the flare. Such flares can have implications for the habitability of surrounding planets, as they would be subjected to intense radiation during flare events. Meanwhile, the cooler temperature of Proxima Centauri means that its habitable zone, where conditions might allow for liquid water on a planet's surface, is much closer to the star compared to our Sun. This has implications for the climates, atmospheres, and potential for life on such planets. As mentioned, stars with temperatures similar to Proxima Centauri's are the most common in our galaxy. This raises interesting prospects for astrobiology, as many of these red dwarfs could host planets. The temperate climates, affected by the cooler stellar temperatures, might present unique conditions for life compared to hotter, sun-like stars. Red dwarfs, given their low temperatures and slow rates of hydrogen fusion, have incredibly long lifespans. They evolve much more slowly than larger stars. In fact, no red dwarf, given their estimated lifetimes, has had enough time since the beginning of the universe to exhaust its hydrogen and evolve into a red giant. This means every red dwarf star we know, including Proxima Centauri, is still in its main sequence phase. The age of Proxima Centauri, much like other stars, can't be determined with pinpoint precision, but astronomers have been able to estimate it based on its characteristics and our understanding of stellar evolution. Proxima Centauri's age is estimated to be between 4.85 billion and 8 billion years old. For context, our Sun is about 4.6 billion years old and is middle-aged in its life cycle. Proxima Centauri, being less massive, evolves more slowly. This means that even if Proxima Centauri formed around the same time as the Sun, it would still be in a much earlier evolutionary stage compared to our Sun. One method of gauging the age of red dwarf stars like Proxima Centauri is by observing their magnetic activity and flare frequency. Younger red dwarfs tend to be more active and have frequent stellar flares, while older ones are calmer. Proxima Centauri does exhibit strong flare activity, suggesting it might be on the younger side of the estimate, but the relationship between age and activity isn't strictly linear and can be influenced by other factors. A 2016 study based on data from the Atacama Large Millimeter Submillimeter Array, ALMA, provided an estimated age range for Proxima Centauri that narrows it down a bit, between 4.4 billion and 6.7 billion years. This was based on observations of the star's rotation and activity levels, as well as comparisons to other, similar stars. However, even with such studies, it's essential to approach the age determination of stars with a degree of caution. The methodologies used have inherent uncertainties, and while they provide a probable age range, they can't pinpoint a precise age. In astronomical terms, metals are elements heavier than helium. The metal content of a star can provide clues about its age. Stars with higher metallicity tend to be younger, having formed later in the universe's history when more heavy elements were available from previous generations of supernovae. The metallicity of Proxima Centauri can provide further context to its age relative to other stars, but determining exact age from metallicity alone is challenging. The metallicity of Proxima Centauri is estimated to be approximately 21% the solar value. However, it's worth noting that different studies might present slightly different figures based on the methodologies and data used. Higher metallicity can indicate that the star formed in a region enriched by previous generations of stars that went supernova. Given Proxima Centauri's relatively low metallicity compared to the Sun, it suggests that Proxima Centauri could have formed in an environment with fewer heavy elements, possibly indicating that it is somewhat older or that it formed in a less metal-rich region of the galaxy. Metallicity can influence planet formation. In general, stars with higher metallicity are more likely to host gas giant planets, as the protoplanetary disk from which planets form would have a greater proportion of heavier elements to build planetesimals and cores of giant planets. Proxima Centauri's metallicity, being lower than the Sun's, might have implications for the types of planets it can form and host. Notably, Proxima Centauri has been found to have at least 2 confirmed planets, of which one is believed to be a gas giant, while the other is an Earth-sized planet in its habitable zone. More on that in a bit. Metallicity can also impact a star's evolution, affecting its temperature, luminosity, and lifespan. Metals influence the opacity of a star's outer layers, which affects energy transport within the star. However, for M-dwarfs like Proxima Centauri, the overall effect of metallicity on the star's lifetime is less pronounced than for more massive stars. Proxima Centauri's rotational period is around 90 days, according to different observations. This rotation rate is significantly slower than that of the Sun, which completes one rotation approximately every 24 to 25 days at its equator. A star's rotational period is closely tied to its magnetic activity. Slower rotation typically results in reduced stellar activity, but Proxima Centauri, despite its lengthy rotation period, exhibits frequent and powerful flares. Stars tend to slow down their rotation as they age due to a process called magnetic braking. Young stars are often rapid rotators, but over time, their magnetic fields interact with the stellar wind, causing them to lose angular momentum and slow down. The relatively long rotation period of Proxima Centauri suggests it's not a very young star, though this is just one piece of the puzzle when determining a star's age. Red dwarfs exhibit a broad range of rotational periods, from just a few hours to several months. Proxima Centauri's rotation period places it on the slower end of this spectrum. With the star's slow rotation and associated magnetic activity, its planets could be subject to different day-night cycles and magnetic interactions compared to what we experience on Earth. There are two main hypotheses regarding the formation of Proxima Centauri in relation to the Alpha Centauri system. Some scientists support the theory that all three stars formed from the same molecular cloud and thus are true siblings. In this scenario, the same processes that led to the formation of the Alpha Centauri binary also led to the formation of Proxima Centauri. It is possible that Proxima was originally closer to the other two stars but was moved to its current position through dynamic interactions during its early history. This theory is supported by the fact that all three stars share a similar motion through space, suggesting a common origin. Another theory suggests that Proxima Centauri formed independently and was later captured by the gravitational force of the main binary. Gravitational capture of a star is a complex process and requires specific conditions, including interaction with a third factor, like another star or group of stars, to provide the necessary energy dissipation to become bound. The case for this scenario is primarily based on the current wide separation between Proxima Centauri and the Alpha Centauri binary system, as well as differences in their properties compared with typical trinary systems. Recent observations tend to support the common origin theory due to the measured velocities and trajectories of the stars, which suggests they are gravitationally bound and have been so for a significant part of their existence. Furthermore, their metallicity also appears to be similar, which is consistent with the stars having formed from the same gas cloud. Ultimately, more detailed observations and models of stellar formation and dynamics, particularly in multi-star systems, are needed to understand fully the complex history of this nearby group of stars. Advances in telescopic technology and space-based observatories in the future may provide further data to clarify the origins of Proxima Centauri within the Alpha Centauri system. Now, let me tell you about the planets of Proxima Centauri. Planets are very common around dwarf stars, with on average 1 to 2 planets per star, and about 20 to 40% of all red dwarfs have one in the habitable zone. Proxima Centauri has one confirmed Earth-like planet, Proxima Centauri b, and 2 more possible planets, Proxima Centauri c and Proxima Centauri d. Proxima Centauri b is one of the most intriguing exoplanets discovered, primarily because of its location in the habitable zone of the closest star to our solar system. Proxima Centauri b was announced in August 2016 after its detection by the European Southern Observatory's HARPS instrument, as well as older data from the Keck Observatory. It was identified using the radial velocity method, where the gravitational effect of the orbiting planet causes slight wobbles in the star's position, leading to observable Doppler shifts in its spectrum. The planet orbits approximately 0.05 astronomical units away from Proxima Centauri. This is just over 7% of the average distance between Earth and our Sun. It completes one orbit around its star in roughly 11.2 Earth days. The minimum mass is about 1.17 times that of Earth, suggesting it's likely a terrestrial or rocky planet. Based on its makeup, Proxima Centauri b might resemble a planet with a substantial core, similar to Mercury, which would be influenced by specific early conditions. Alternatively, it could be abundant in water. Studying the ratios of iron, silicon, and magnesium in Proxima Centauri could help discern the planet's composition, as these ratios in the star are anticipated to mirror those in its planetary bodies. Notably, several studies have identified ratios of these elements in Proxima Centauri that are comparable to those in our solar system. Proxima Centauri B's formation conditions probably varied from Earth's, with it possibly having less water, experiencing more intense impacts, and undergoing a quicker developmental phase, especially if it originated at its present proximity to its star. It's improbable that Proxima Centauri b formed at its existing location due to an anticipated lack of material in the protoplanetary disk. More likely, the planet or its early fragments originated farther out and later shifted to its current orbit. The precursor materials could be rich in volatile compounds, depending on their nature. The planet is situated within Proxima Centauri's habitable zone, sometimes termed the Goldilocks zone. This is the region around a star where conditions might be just right for liquid water to exist on a planet's surface, assuming the planet has a suitable atmosphere. However, the habitable zone around a red dwarf like Proxima Centauri is much closer to the star than it would be around a Sun-like star, due to the red dwarf's lower luminosity. Since Proxima Centauri is known for frequent stellar flare-ups emitting high-energy radiation, those flares could strip away a planet's atmosphere or make conditions challenging for potential life forms. Initial studies for Proxima Centauri b suggest it has a low eccentricity, close to a circular orbit. Eccentricity refers to the shape of an object's orbit around another object, usually measured in relation to a perfect circle. An eccentricity of 0 denotes a perfectly circular orbit, while values closer to 1 indicate more elongated elliptical orbits. However, the exact value might have some uncertainties and could be refined with more detailed observations and data analysis. Obliquity refers to the tilt of a planet's rotational axis in relation to its orbital plane. For context, Earth has an axial tilt, or obliquity, of about 23.5 degrees, which results in our seasonal variations. The obliquity of Proxima Centauri b is not firmly established. Determining the obliquity of exoplanets, especially those around distant stars, is a challenging task requiring precise measurements and often advanced methods like analyzing the polarized light from the star-planet system. Both the eccentricity and obliquity can have significant effects on the climate and potential habitability of a planet. For instance, a high obliquity could result in extreme seasonal variations. Similarly, a significant orbital eccentricity might lead to substantial temperature differences between the planet's closest and farthest points from its star. Due to its close proximity to its host star, Proxima Centauri b is believed to be in a 1-to-1 tidal lock. This means one side of the planet, the day side, constantly faces the star, while the other side, the night side, is in perpetual darkness. In this regard, Professor Avi Loeb has famously stated many times, his daughters speculate the real estate prices should be high in the twilight zone. Such a locking mechanism could challenge the establishment of habitable conditions, leading to an extreme climate where only portions of the planet are livable. Nevertheless, Proxima Centauri b might not be tidally locked in a 1-to-1 tidal lock. If its eccentricity exceeded about 0.1, the planet could adopt a 3-to-2 resonance, similar to Mercury, or even higher resonances like 2-to-1. The presence of other planets around Proxima Centauri or interactions with the Alpha Centauri system could induce greater eccentricities. If Proxima Centauri b isn't perfectly symmetrical, it might maintain a non-tidally locked orbit even at low eccentricities. However, such an orbit could cause the planet's mantle to experience tidal heating, potentially increasing its volcanic activity and possibly hindering the generation of a magnetic field. The specific behaviors would largely depend on the planet's internal makeup and its reaction to tidal forces. If you were standing on the surface of Proxima Centauri b and looking up at Proxima Centauri, the experience would be quite different from viewing the Sun from Earth, primarily due to the differing distances, sizes, and brightnesses of the two stars. Proxima Centauri is a much smaller star than the Sun, but Proxima Centauri b orbits it much more closely than Earth orbits the Sun. This closer distance would make Proxima Centauri appear larger in the sky of Proxima Centauri b than the Sun appears in Earth's sky. The exact size difference would depend on the precise orbital distance, but it's likely that Proxima Centauri would occupy a significantly larger portion of the sky. The starlight from Proxima Centauri would give the sky of Proxima Centauri b a redder hue compared to the yellowish light we're used to on Earth. However, because of the close proximity of the planet to the star, the overall brightness might be similar to or even exceed that of daytime on Earth, despite the star's intrinsic dimness compared to the Sun. During a flare, the brightness of the star can change suddenly. An observer on Proxima Centauri b might experience sudden, dramatic increases in brightness when the star flares, which could impact the perceived daylight conditions. The presence and composition of an atmosphere around Proxima Centauri b are still topics of investigation. An atmosphere is crucial for regulating a planet's surface temperature and could play a pivotal role in its habitability. While its location in the habitable zone raises the possibility of liquid water, direct evidence of water on the planet's surface hasn't been confirmed. The potential for exoplanets, like Proxima Centauri b, to host moons, exomoons, is a topic of active interest in the field of astronomy. The proximity of Proxima Centauri b to its star, with an orbital distance of roughly 0.05 astronomical units, might impact the stability of potential exomoons' orbits. Tidal forces exerted by the star could lead to significant challenges in maintaining a stable orbit for any moon over long timescales. Moons can form in various ways, such as through the co-accretion with their host planet, capture of wandering celestial bodies, or from the debris resulting from a significant impact. Depending on the early environment and history of the Proxima Centauri system, any of these processes could potentially have led to moon formation. Detecting exomoons is an enormous challenge. Most exoplanet detection methods, such as the radial velocity or the transit method, are tailored to find planets, which are more massive than moons and thus have a more noticeable effect on their host star or the star's light. As of yet, no exomoons has been confirmed definitively of any exoplanet. If Proxima Centauri b does host a moon, it could have implications for the planet's habitability. For instance, Earth's moon stabilizes our planet's axial tilt, which helps maintain relatively stable climatic conditions. A moon could also affect tidal forces, potentially impacting geological activity or even ocean dynamics if the planet has liquid water. The composition of Proxima Centauri b's atmosphere, if it has one, would be crucial for determining its surface conditions, including temperature and pressure, as well as potential habitability. Given the high-energy radiation environment from Proxima Centauri, a thick atmosphere or strong magnetic field might be necessary to protect any potential life on the planet's surface. The presence of an atmosphere and the ability to retain water are essential for liquid water to exist on the surface. Some models have suggested that if Proxima Centauri b had an Earth-like atmosphere and appropriate starting water reserves, it could have liquid water on its surface, at least in some regions. Proxima Centauri b receives significantly more UV and X-ray radiation compared to Earth due to its close proximity to its host star. Proxima Centauri has a quiescent X-ray luminosity similar to that of the Sun, but it can emit powerful flares that boost its X-ray luminosity by over 100 times on occasion. Due to its close orbit, Proxima Centauri b is exposed to X-ray fluxes that are over 400 times those experienced by Earth. The UV radiation on Proxima Centauri b is also much higher compared to Earth. Studies estimate that the UV flux on Proxima Centauri b is about 250 times greater than what Earth receives from the Sun. During intense flaring events, this UV flux can temporarily increase to thousands of times the UV flux on Earth. This heightened UV and X-ray radiation from Proxima Centauri can have numerous consequences for Proxima Centauri b's atmosphere and potential habitability. The intense radiation can erode the planet's atmosphere over time and would pose challenges for any potential life forms to survive on the surface, especially without some form of protection, such as a sufficiently thick atmosphere or subsurface aquatic environments. However, UV radiation on Proxima Centauri b is redder, colder, in comparison to X-UV radiation, potentially interacting less with organic compounds and possibly resulting in reduced ozone production. What about the larger planet, Proxima Centauri c? Proxima Centauri c was announced in 2020, following observations using the radial velocity method as well as direct imaging. The latter is quite rare in exoplanet discoveries due to the challenges of distinguishing a planet from the glare of its host star, making the detection of Proxima Centauri c particularly notable. However, a study in 2022 cast doubt on the planetary status of the observed radial velocity signal related to Proxima c, attributing it to systematic effects. Under this scenario, it becomes ambiguous as to why astrometric observations seemingly detected a comparable planetary signature. Proxima Centauri c is suggested to orbit at a distance of about 1.5 astronomical units from Proxima Centauri. This is roughly 1.5 times the average distance between Earth and our Sun. It completes one orbit around Proxima Centauri in about 5.2 Earth years. Considering Proxima Centauri is about 500 times less luminous than the Sun, unless there are strong factors keeping the planet warm, like strong greenhouse effects, the surface of the planet must be very cold. Proxima Centauri c has a suggested minimum mass of about 7 times that of Earth. This categorizes it as a super-Earth or potentially a mini-Neptune, given its mass range. An image capturing Proxima Centauri c was taken using the SPHERE instrument on the Very Large Telescope, VLT, operated by the European Southern Observatory, but the picture is incongruent with the mass previously suggested for the planet, unless something else is going on, like a massive ring system around it. While Proxima Centauri b's location in the habitable zone makes it a prime target for studies on habitability, the discovery of Proxima Centauri c added depth to our understanding of the Proxima Centauri system. Multiple planet systems can offer insights into planetary formation, migration, and interactions. Then you have the candidate planet of Proxima Centauri d. Characterized as a sub-Earth, Proxima Centauri d has a minimum mass of a quarter that of Earth, or double that of Mars, and completes an orbit around its star approximately every 5.1 days at a distance of about 0.029 astronomical units. This makes it the least massive and innermost known planet in the Proxima Centauri system and, as of 2022, the least massive exoplanet detected via the radial velocity method. Despite its close orbit to its star resulting in a likely non-habitable equilibrium temperature, estimated around 360 Kelvin, there's a theoretical possibility that Proxima Centauri d could have habitable temperatures in its polar regions. Specific details about Proxima Centauri d, such as its mass, orbital period, and distance from the star, are not firmly established. To determine whether Proxima Centauri d is a genuine planet, rather than a result of observational noise or other phenomena, astronomers will need to gather more data and possibly utilize other detection methods. Advances in telescope technology and improved observational campaigns will play a pivotal role in this effort. Let us now move on to focus on the two separate stars of the main binary, Rigil, Kentaurus and Toliman. As mentioned earlier, the apparent magnitude of a star is a measure of the star's brightness as seen from Earth. The lower the number, or into the negative, the brighter the star appears. Rigil Kentaurus has an apparent magnitude of -0.01, making it the third brightest star in Earth's night sky, surpassed only by Sirius and Canopus. Toliman has an apparent magnitude of +1.33, making it the 21st brightest star in our night sky, which is also quite luminous considering how many stars we can see. About 5,000 stars are visible to the naked eye in good viewing conditions. However, as previously said, the human eye cannot separate Rigil, Kentaurus and Toliman from each other as separate stars, making it in fact look like one even brighter star. Rigil Kentaurus is slightly bigger and Toliman slightly smaller than our Sun. Intriguingly, together, the main binary is quite close to possessing exactly 2 times the mass of the Sun. Specifically, Rigil Kentaurus has about 1.1 solar masses. Toliman, on the other hand, possesses about 0.91 solar masses. The difference in mass entails a difference in gravitational pull. The gravity influences the star's physical properties and life cycle, impacting how it burns fuel and evolves over time. Stars with greater mass generally have shorter lifespans than their lower mass counterparts, because they consume their nuclear fuel at a faster rate. Therefore, even though Rigil Kentaurus is somewhat similar to the Sun, its higher mass means that its life cycle will unfold differently, burning through its stellar fuel more quickly and evolving to the next stage of its stellar life at a quicker pace. Stars with a lower mass, like Toliman, burn through their nuclear fuel more slowly and therefore tend to have longer lifespans. Rigil Kentaurus has a radius that is approximately 1.2 times that of the Sun. The radius of Toliman is approximately 0.86 solar radii. The different sizes contributes to their respective luminosities. Rigil Kentaurus is about 1.5 times more luminous than the Sun, meaning it emits significantly more light and energy into space than our Sun does, while Toliman affords a luminosity about 0.5 times that of the Sun. The size and luminosity of each star affect the location of their habitable zones, the regions where conditions might allow the existence of liquid water on a planet's surface, which is crucial in the search for potentially habitable exoplanets. Let us look closer at what types of stars Rigil Kentaurus and Toliman are. They are both main sequence stars. The term main sequence refers to the phase in a star's life where it is primarily converting hydrogen into helium through nuclear fusion in its core. Stars during this phase are located along the main sequence on the Hertzsprung-Russell diagram, which is a graph plotting stars' luminosity versus their temperature, or color. Most stars, including our Sun, spend the majority of their lives in the main sequence phase. Rigil Kentaurus is of spectral type G2V, while Toliman is of spectral type K1V. The classifications refers to specific characteristics regarding luminosity class, and consequently, color, temperature, and evolutionary stage. G-type stars, like Rigil Kentaurus, are characterized by their yellow color, which is caused by the absorption of ionized metals, such as calcium and iron, as well as neutral metals, such as sodium. They have surface temperatures between 5,300 and 6,000 Kelvin. K-type stars, like Toliman, are cooler than our Sun and have a somewhat orangish color. They possess a temperature that typically falls between 3,700 and 5,200 Kelvin. K-type stars also demonstrate particular absorption lines in their spectrum, attributed mainly to neutral metals and certain molecular bands. The numerals 2, for Rigil Kentaurus, and 1, for Toliman, represents a subdivision of the spectral type, providing more detailed information about the star's temperature. The scale runs from 0, the hottest, to 9, the coolest, within a given spectral type. V, or Roman numeral 5, represents the luminosity class of the star. V indicates that the star is a main sequence star, as opposed to a giant or supergiant star. Rigil Kentaurus has an effective surface temperature of approximately 5,800 Kelvin. This temperature is very similar to that of our Sun, which is also a G2V star, and has a surface temperature of about the same. The color of Rigil Kentaurus is yellowish-white, which is typical for G-type stars. The color is a visual representation of the temperature and spectral class of the star. The yellowish-white color indicates that it's cooler than bluer stars, like O or B-type stars, but hotter than redder stars, like M-type stars. The color and temperature also influence the type of radiation it emits. While Rigil Kentaurus emits across a broad spectrum, it peaks in visible light, which is part of the reason it appears so bright in our sky. With an effective surface temperature of approximately 5,200 Kelvin, Toliman is slightly cooler than our own Sun. Toliman emanates an orange hue, which is predominantly attributed to its lower surface temperature relative to hotter stars. The cooler temperature of Toliman results in its color being shifted towards the red end of the visible spectrum, which is in accordance with Wien's law, illustrating the inversely proportional relationship between the peak wavelength of emitted light and the absolute temperature of the star. Together, the color contrast in the Alpha Centauri binary system is subtle yet discernible. As stars age, they undergo subtle but significant changes in their physical properties, such as luminosity and temperature, often making older stars more luminous as they exhaust the hydrogen at their cores. Astronomers estimate the age of Rigil Kentaurus to be between 4.5 and 7 billion years. They similarly estimate the age of Toliman to be between 4.0 and 6.3 billion years. Given this age range, both Rigil Kentaurus and Toliman could be slightly older than our Sun, which is about 4.6 billion years old. The Sun and Rigil Kentaurus in particular are intriguingly similar in several ways. Both are categorized as G-type stars, with comparable temperatures, colors, and, potentially, ages. This similarity has prompted some astronomers to explore the possibility of a shared origin or a connection between the two stars. In the Milky Way galaxy, stars often form within large, dense clouds of gas and dust known as stellar nurseries. It's plausible that the Sun and Rigil Kentaurus could have originated in the same stellar nursery, given their similarities and relatively close proximity on a cosmic scale, about 4.34 light-years apart. Stars that form together in this way are often referred to as sibling stars. However, it's essential to highlight that proving a shared origin for stars is a complex and challenging task. Astronomers can analyze stars' chemical compositions, trajectories, and velocities through space to deduce potential common origins, but absolute confirmation can be elusive. There have been investigations into potential sibling stars of the Sun, that is, stars that formed from the same molecular cloud, but Rigil Kentaurus has not been conclusively identified as one. Both Rigil Kentaurus and Toliman have rotational periods of about 30 days. This is notably similar to our own Sun, which has an average rotational period of approximately 24 days at its equator. This similarity is of particular interest because the rotational period of a star is correlated with various stellar characteristics, such as its magnetic activity and age. Stars like Rigil Kentaurus, Toliman, and the Sun show a pattern where their rotation gradually slows down as they age, due to the loss of angular momentum through stellar winds over time. Rigil Kentaurus has a somewhat stable magnetic activity, and its similarity to the Sun extends beyond its classification and includes aspects of its activity cycle. For instance, it has a solar cycle characterized by the periodic variation in its activity, including changes in the levels of radiation emitted, the ejection of stellar material, and the appearance of sunspots, which is somewhat analogous to the Sun's own 11-year cycle. However, detailed observational data and further study might reveal nuances in its behavior, shedding light on the spectrum of activities across stars of similar classification and attributes. Rigil Kentaurus and Toliman are known to exhibit magnetic activity, X-ray emissions, and flaring, much like our own Sun, albeit with some differences in frequency and intensity due to their distinct stellar characteristics. Rigil Kentaurus does emit X-rays, but notably, its X-ray luminosity is lower than the Sun's, reflecting a relatively quiescent X-ray behavior. As mentioned, it has a magnetic cycle somewhat analogous to the Sun's 11-year sunspot cycle. Its magnetic field has been studied through variations in its Ca2H and K lines, which are indicative of magnetic activity. Flares have been observed, but Rigil Kentaurus tends to have a relatively stable luminosity and doesn't exhibit flaring as prolifically as its smaller companion, Toliman. Toliman is a stronger X-ray emitter than Rigil Kentaurus. Its higher level of X-ray emission is indicative of a more pronounced magnetic activity, characteristic of K-type stars, which often have more active magnetic dynamos than their G-type counterparts. The magnetic activity of Toliman is more vigorous compared to Rigil Kentaurus, with a somewhat shorter magnetic cycle of around 8 years. This heightened activity is also manifested in its flare activity and X-ray emissions. Toliman exhibits stellar flares more frequently than Rigil Kentaurus. These flares are sudden, brief increases in brightness, associated with magnetic activity on the star's surface and often tied to the interaction of magnetic field lines. The magnetic activity and related stellar phenomena, such as flares and X-ray emissions, of a star can have significant implications for the habitability of any surrounding planets. Flares and X-ray emissions can influence a planet's atmosphere, affecting its ability to retain essential elements for habitability and potentially posing challenges for any potential life forms with regards to radiation exposure. Metallicity in astronomical terms was mentioned before with regard to Proxima Centauri. It refers to the proportion of a star's mass that is not hydrogen or helium, essentially accounting for all heavier elements. In stellar astronomy, this is a critical parameter because it can impact the star's evolution, its likelihood to host planets, and the type of planets it may form. Rigil Kentaurus has a metallicity slightly higher than that of the Sun. Estimates of its metallicity value have varied but tend to be close to or slightly above solar, meaning it has a somewhat higher proportion of elements heavier than hydrogen and helium than our Sun does. The somewhat higher metallicity suggests a rich environment of elements necessary for forming planetary bodies. The presence of heavier elements can be crucial for the formation of terrestrial planets. The metallicity of Toliman is somewhat similar to that of Rigil Kentaurus, albeit with some variations depending on the precise measurements and methods used. Generally, it is also considered to have a metallicity close to or slightly above that of the Sun. Similar to Rigil Kentaurus, the metallicity of Toliman hints at a potential for planet formation due to the availability of heavier elements, which are critical in the formation of rocky planets. Now, what do we know about exoplanets around Rigil Kentaurus or Toliman? In 2021, an observation of a potential exoplanet termed Candidate 1, or C1, was suggested to orbit Rigil Kentaurus. The proper naming of the candidate will, if it is confirmed, B Alpha Centauri AB, in accordance with the tradition of the International Astronomical Union. Intriguingly, considering the similar properties of the Sun and Rigil Kentaurus, the candidate was suggested to orbit at a distance of 1.1 astronomical units and with a period of 360 days, very similar to Earth's orbit around the Sun. There have been suggestions, however, of C1 being something else, like a colossal, gaseous planet, a mere dust cloud, or a statistical anomaly in the data, like a distant star aligning with Rigil Kentaurus from our vantage point, but some of these have been ruled out through meticulous background analysis. Pre-launch simulations for the James Webb Space Telescope, JWST, have hinted at its prowess in unearthing planets as large as 5 Earth radii, possibly lurking between 1 and 3 astronomical units from their parent star. Periodic, dedicated surveillance spaced every few months could refine JWST's sensitivity, bringing smaller worlds of at least 3 Earth radii into its view. Advanced data crunching post-observation techniques might even reveal planets as minute as half to 7/10 of Earth's size, enhancing JWST's planet hunting acumen. Bolstered by these projections and initial findings, the astronomical community is hopeful that JWST's capabilities could penetrate even closer to Rigil Kentaurus. It might discern planets up to 5 Earth radii in size, potentially hiding anywhere from 0.5 to 2.5 astronomical units from the star. Considering these prospects, Candidate 1, with its estimated size ranging from 3.3 to 11 Earth radii, residing at 1.1 astronomical units, seems well within JWST's observational grasp. Thus, all eyes are on JWST, as its upcoming endeavors might confirm C1's existence and, in the process, enrich our understanding of the cosmic neighborhood. There have also been some observations suggesting candidates around Toliman. In 2012, researchers announced the detection of a candidate in the vicinity of Toliman. However, by 2015, subsequent reviews suggested that the initial identification was likely a data analysis misinterpretation. Separately, in 2013, observers noted a potential transit event, hinting at the presence of another planetary object. This prospective body might possess a radius roughly equivalent to 0.92 Earth radii. The characteristics suggest a relatively close orbit to Toliman, necessitating 20.4 days or potentially fewer for a full orbit, though there's a slim possibility, 5%, of a more extended orbital duration. The most probable orbit median stands at 12.4 days. Additionally, the orbit's eccentricity is predicted to be no more than 0.24. The proximity to its star suggests a hostile environment, potentially featuring molten lava surfaces, certainly not conducive to life as we know it. Should further investigations confirm its existence, the protocol might designate this planet as Alpha Centauri BC. However, as of 2023, this nomenclature hasn't appeared in scholarly articles, primarily because there hasn't been a formal claim of discovery. Moreover, there seem to be no additional sightings of similar transit-like events to bolster the 2013 observations. The binary nature of the Alpha Centauri system does add complexity to the process of planet formation and the subsequent dynamics of any planets that do form. The gravitational forces in a binary or multiple star system are significantly more complex than those around a single star. During the early stages of system formation, the gravitational pull of the two central stars would influence the circumstellar disk's material, potentially making the process of planetesimal and protoplanet formation more chaotic and collision-rich. Depending on the star's proximity, their gravitational forces could either help collect material into larger bodies or disrupt the process, causing material to collide at high speeds, fragmenting into smaller pieces, or be ejected from the system. In binary systems, stable orbits for planets are typically closer to each of the individual stars or far enough away to orbit the binary system's center of mass. These stable regions, known as circumstellar habitable zones for habitable orbits around a single star, and circumbinary habitable zones for habitable orbits around both stars, are critical for long-term planetary stability in habitable zones. In the case of Alpha Centauri, the two main stars, Rigil, Kentaurus and Toliman, are relatively far apart, with an average distance of about 23 astronomical units between them. This distance allows for stable orbiting regions around each star, where planets could exist without excessive gravitational disruption from the other star. If planets do form in stable orbits within the habitable zone of their star, the binary nature could still influence habitability. For instance, varying distances from the companion star during the planet's orbit could result in significant temperature fluctuations, affecting the planet's climate and atmospheric conditions. However, if a planet maintains a stable orbit and sufficient distance from the binary system's gravitational center, it could potentially retain its atmosphere and possibly host life-sustaining conditions, akin to Earth's. While the binary nature presents challenges and unique conditions for planet formation and stability, it doesn't preclude the possibility. The discovery of exoplanets in various types of star systems, including binary systems, throughout our galaxy indicates that planet formation can be quite versatile and resilient to a range of stellar environments. Now, let us look around from our new vantage point. What's the view like from Alpha Centauri? From the vantage point of Proxima Centauri, its larger companion stars, Rigil, Kentaurus and Toliman, would appear as two distinctly bright stars in the sky. Rigil Kentaurus would be the brightest of the two, because it is larger and emits more light than Toliman. A viewer might also observe a distinct color contrast between the two stars. Rigil Kentaurus would exhibit a yellowish-white hue due to its G-type star classification, while Toliman would shine with a more orange tint, being a K-type star. Viewing one star from another within the Alpha Centauri main binary system would be a significantly different experience from observing stars in Earth's night sky. From either star, the other would appear as an extremely bright star in the sky, far outshining any other star or planet visible from that vantage point. They wouldn't look like the small pinpoints of light we see when we look at stars from Earth. Instead, they would appear as small disks, much like how we see the Sun from Earth, but smaller. The companion star would be visible both during the day and the night, depending on your location on the hypothetical planet you're viewing from. During the day, it would appear as a second sun, albeit much less intense than the primary star, creating unique dual shadow effects. At night, if you were on the side of the planet facing away from your primary star, the companion star would be a dominant light source, significantly brighter than the full moon is on Earth, potentially bright enough to diminish the visibility of other celestial objects. The Alpha Centauri system is not a static one. The two stars orbit each other approximately every 80 years in ellipses. This means the apparent size, brightness, and position in the sky of each star, as seen from the other, would change over those years. They would appear closest and largest at periastron, when they are nearest to each other in their orbits, and smallest and faintest at epastron, their most distant point. These changes would occur slowly, over decades, but they would be quite noticeable over a human lifetime. In essence, from a planet orbiting one of the stars, the other star would be a remarkably bright, dominant, and dynamic fixture in the sky, contributing significantly to the natural light environment and possibly influencing the rhythms of any life forms that might emerge on orbiting planets. If you were in a planetary shadow of both stars and gazing toward our Sun, you would see a star shining with an apparent magnitude of approximately 0.4. This brightness is comparable to some of the stars we observe from Earth on a clear night. For a reference point, it's slightly dimmer than the star Mimosa in the Southern Cross, as seen from Earth. The Sun would still appear as a white or yellowish-white star, consistent with the G-type main sequence star that it is. The Sun would be situated within the zodiac constellation of Cassiopeia. Therefore, if you were on a planet orbiting one of the stars in the Alpha Centauri system, the Sun would be a consistent point in your night sky, embedded within this well-recognized constellation. You would still recognize many of the same constellations in the night sky, albeit with slight variations. Given Alpha Centauri is located towards the center of the Milky Way, if viewed from Earth, you would be gazing in the opposite direction, that is, roughly outward from the center of the Milky Way galaxy, toward a less densely packed region. If you are still awake and want more content, go ahead and check out our other episodes, and if you want to help creating even more, please consider supporting us. While this manuscript was written by AI and read by me, an AI voice, creating this content still required production time from a human being. If you want to support the production, please make a donation to the Milky Way Traveler over at Patreon. To do so, follow the link in the show notes or search for the Milky Way Traveler at Patreon. If anything is incorrect in this episode, if you are missing some information, or if you just want to add your view, feel free to make a comment in the comment section for this episode. Now, thank you for joining this trip, and have a beautiful and wonderful night, with sweet dreams, once you get there.